In electronics, a linear regulator is a system used to maintain a steady voltage. The resistance of the regulator varies in accordance with the load, resulting in a constant output voltage. The regulating device is made to act like a variable resistor, continuously adjusting a voltage divider network to maintain a constant output voltage, and continually dissipating the difference between the input and regulated voltages as waste heat. By contrast, a switching regulator uses an active device that switches on and off to maintain an average value of output. Because the regulated voltage of a linear regulator must always be lower than input voltage, efficiency is limited and the input voltage must be high enough to always allow the active device to drop some voltage. Linear regulators may place the regulating device in parallel with the load or may place the regulating device between the source and the regulated load. Simple linear regulators may only contain a Zener diode and a series resistor. More complicated regulators include separate stages of voltage, reference, error amplifier and power pass element. Because a linear voltage regulator is a common element of many devices, integrated circuit regulators are very common. Linear regulators may also be made up of assemblies of discrete solid-state or vacuum tube components. Overview. The transistor is used as one half of a potential divider to establish the regulated output voltage. The output voltage is compared to a reference voltage to produce a control signal to the transistor which will drive its gate or base. With negative feedback and good choice of compensation, the output voltage is kept reasonably constant. Linear regulators are often inefficient. Since the transistor is acting like a resistor, it will waste electrical energy by converting it to heat. In fact, the power loss due to heating in the transistor is the current multiplied by the voltage difference between input and output voltage. The same function can often be performed much more efficiently by a switched-mode power supply, but a linear regulator may be preferred for light loads or where the desired output voltage approaches the source voltage. In these cases, the linear regulator may dissipate less power than a switcher. The linear regulator also has the advantage of not requiring magnetic devices which can be relatively expensive or bulky, being often of simpler design, and being quieter. Some designs of linear regulators use only transistors, diodes and resistors, which are easier to fabricate into an integrated circuit, further reducing their weight, footprint on a PCB, and price. All linear regulators require an input voltage at least some minimum amount higher than the desired output voltage. That minimum amount is called the dropout voltage. For example, a common regulator such as the 7805 has an output voltage of 5V, but can only maintain this if the input voltage remains above about 7V, before the output voltage begins sagging below the rated output. Its dropout voltage is therefore 7V minus 5V equals 2V. When the supply voltage is less than about 2V above the desired output voltage, as is the case in low-voltage microprocessor power supplies, so-called low dropout regulators must be used. When the output regulated voltage must be higher than the available input voltage, no linear regulator will work. In this situation, a switching regulator of the boost type must be used. Most linear regulators will continue to provide some output voltage approximately the dropout voltage below the input voltage for inputs below the nominal output voltage until the input voltage drops significantly. Linear regulators exist in two basic forms: shunt regulators and series regulators. Most linear regulators have a maximum rated output current. This is generally limited by either power dissipation capability or by the current carrying capability of the output transistor. Shunt regulators. The shunt regulator works by providing a path from the supply voltage to ground through a variable resistance. The current through the shunt regulator is diverted away from the load and flows uselessly to ground, making this form usually less efficient than the series regulator. It is, however, simpler, sometimes consisting of just a voltage reference diode, and is used in very low-powered circuits where the wasted current is too small to be of concern. This form is very common for voltage reference circuits. A shunt regulator can usually only sink current. Series regulators are more common form. The series regulator works by providing a path from the supply voltage to the load through a variable resistance. The power dissipated by the regulating device is equal to the power supply output current times the voltage drop in the regulating device. A series regulator can usually only source current. Simple shunt regulator. The image shows a simple shunt voltage regulator that operates by way of the Zener diode's action of maintaining a constant voltage across itself, when the current through it is sufficient to take it into the Zener breakdown region. The resistor R1 supplies the Zener current as well as the load current IR2. R1 can be calculated as, whereas the Zener voltage, and IR2 is the required load current. This regulator is used for very simple low-power applications where the currents involved are very small and the load is permanently connected across the Zener diode. Once R1 has been calculated, removing R2 will allow the full load current through the diode and may exceed the diode's maximum current rating, thereby damaging it. The regulation of this circuit is also not very good because the Zener current will vary depending on and inversely depending on the load current. In some designs, the Zener diode may be replaced with another similarly functioning device, especially in an ultra-low voltage scenario, like several normal diodes or LEDs in series. Simple series regulator. Adding an emitter-follower stage to the simple shunt regulator forms a simple series voltage regulator and substantially improves the regulation of the circuit. Here, the load current IR2 is supplied by the transistor whose base is now connected to the Zener diode. Thus, the transistor's base current forms the load current for the Zener diode and is much smaller than the current through R2. This regulator is classified as series because the regulating element, viz., the transistor, appears in series with the load. R1 sets the Zener current and is determined as where Vz is the Zener voltage, Ib is the transistor's base current, K equals 1.2 to 2, and where IR2 is the required load current and is also the transistor's emitter current, and HFE is the minimum acceptable DC current gain for the transistor. This circuit has much better regulation than the simple shunt regulator, since the base current of the transistor forms a very light load on the Zener, thereby minimizing variation in Zener voltage due to variation in the load. Note that the output voltage will always be about 0.65 V less than the Zener due to the transistor's VBE drop. Although this circuit has good regulation, it is still sensitive to the load and supply variation. This can be resolved by incorporating negative feedback circuitry into it. This regulator is often used as a pre-regulator in more advanced series voltage regulator circuits. The circuit is readily made adjustable by adding a potentiometer across the Zener, moving the transistor base connection from the top of the Zener to the pot wiper. It may be made step adjustable by switching in different Zeners. Finally, it is occasionally made micro-adjustable by adding a low-value pot in series with the Zener. This allows a little voltage adjustment, but degrades regulation. Fixed regulators. Fixed, three-terminal linear regulators are commonly available to generate fixed voltages of plus 3V, and plus or minus 5V, 6V, 9V, 12V, or 15V, when the load is less than 1.5 A. The 78XX series regulate positive voltages while the 79XX series regulates negative voltages. Often, the last two digits of the device number are the output voltage. There are variants on the 78XX series ICs, such as 78L and 78S, some of which can supply up to 2 amps. Adjusting fixed regulators by adding another circuit element to a fixed voltage IC regulator, it is possible to adjust the output voltage. 2 example methods are, a Zener diode or resistor may be added between the IC's ground terminal and ground. Resistors are acceptable where ground current is constant, but are ill-suited to regulators with varying ground current. By switching in different Zener diodes or resistors, the output voltage can be adjusted in a stepwise fashion. A potentiometer can be placed in series with the ground terminal to increase the output voltage variably. However, this method degrades regulation, and is not suitable for regulators with varying ground current. Variable regulators. An adjustable regulator generates a fixed low nominal voltage between its output and its adjust terminal. This family of devices includes low-power devices like LM723 and medium-power devices like LM317 and L200. Some of the variable regulators are available in packages with more than 3 pins, including dual inline packages. They offer the capability to adjust the output voltage by using external resistors of specific values. For output voltages not provided by standard fixed regulators in load currents of less than 7A, commonly available adjustable 3-terminal linear regulators may be used. The LM317 series regulates positive voltages while the LM337 series regulates negative voltages. The adjustment is performed by constructing a potential divider with its ends between the regulator output and ground, and its center tap connected to the adjust terminal of the regulator. The ratio of resistances determines the output voltage using the same feedback mechanisms described earlier. Single IC dual tracking adjustable regulators are available for applications such as op-amp circuits needing matched positive and negative DC supplies. Some have selectable current limiting as well. Some regulators require a minimum load protection. Linear IC voltage regulators may include a variety of protection methods. Current limiting such as constant current limiting or foldback. Thermal shutdown. Safe operating area protection. Sometimes external protection is used, such as crowbar protection, using a linear regulator. Linear regulators can be constructed using discrete components but are usually encountered in integrated circuit forms. The most common linear regulators are 3-terminal integrated circuits in the TO220 package. Common solid-state series voltage regulators are the LM78XX, LM79XX, and the AMS1117 series. Common fixed voltages are 1.8V, 3.3V, 5V and 12V. In fixed voltage regulators the reference pin is tied to ground, whereas in variable regulators the reference pin is connected to the center point of a fixed or variable voltage divider fed by the regulator's output. A variable voltage divider such as a potentiometer allows the user to adjust the regulated voltage